Hello, everyone. We're Team 2, and our project this summer focused on understanding and predicting urban heat islands throughout Durham and Raleigh. Urban heat islands are specific areas within cities or urban areas where the temperature is notably higher than the surrounding rural areas or natural environments. This occurs due to the presence of modern infrastructure such as buildings, roads, and parking lots, which tend to absorb and retain more heat compared to natural elements like trees and grass. In order to understand how drastic this effect can be, this map of Raleigh from July 2021 shows that certain areas were over 10 degrees hotter than others, which is an extremely significant difference to have in one city on the same day. To begin to address this issue, our plan was to first create a model that understands the impacts of landscape modifications on local temperatures so that we can predict the extent of the urban heat island effect in certain areas. Then, this model was used to analyze potential interventions that can decrease the temperatures in the most affected areas and serve as a starting point for greater policy change. Our model was created from data regarding vegetation index, satellite imagery, temperature measurements, and land cover classifications. The first part of our model was created using k-means to segment our satellite images by land cover type. Then we used gradient boosting regression to combine this segmentation with vegetation and temperature. The second half of our model focused on predicting the residuals of our initial model to understand how well it was accounting for spatial confounding. Then, by combining the two, we were able to create our final product, which is a regression Kriging model.
Now, the first graph in the middle column is an actual satellite image of part of Raleigh. Below it, we have the temperature predictions from the regression Kriging model, which is a combination of the previously mentioned gradient boosting model and Kriged residuals model. Roughly, we can see the greener areas tend to have lower temperatures, and areas with higher population density tend to have higher temperatures, which makes sense intuitively. So we assessed our model performance by looking at the test R-squared score. For the gradient boosting model, we got an R-squared of 0.5, which means it explains half of the variance. It's pretty good, but not good enough. So we used the Kriged residuals model to learn the residuals coming out of gradient boosting model, and we got an R-squared of 0.87. Combining the two models, our final model has an R-squared of 0.95, which is very good. So now we're able to look at intervention strategies. We implemented 5 different intervention strategies, and one example is called priority areas with buffer zones. So basically, we identified areas that are among the hottest but have low vegetation coverage. They are our priority areas. We then include its surroundings with a radius of 100 meters, and it simulates the buffer zones. So then we increase the vegetation index of these areas, and here is the result. As you can see, the temperatures decrease by 0 to 4 degrees, and the temperatures of about half of the areas decrease by more than 2 degrees. We think this is actually pretty impressive. Next, we want to discuss what could be done in the future. First, we want to further investigate the nonlinear relationship between intervention and temperature. We also want to explore applying this framework to more cities. Last but not least, we want to link changes to urban heat islands with changes to energy consumption and health outcomes. And that's pretty much everything. Thank you for watching.